Testing regression errors for normality. One of the assumptions of classical linear regression model is that errors are normally distributed. This lecture is devoted to test this normality assumption on some real-world data. It is important to note that true errors, like true regression parameters, are unknown and unobserved. So normality of true errors cannot be established. Hence, this assumption is generally tested on OLS residuals which are observed, and they can be calculated based upon some sample data. A normal distribution has many features. First one, it is unimodal with a bell-shaped center. So here it has only one mode with the center at 0. It is symmetric around the mean. The mean is 0 in this case. We can see that the shape on the left of this 0 is same as the shape on the right of the 0. So this indicates the symmetric property, and this line is called line of symmetry or axis of symmetry. Its tails are exponentially declining, so this is called the left tail, this one is called right tail. We can see that the tails are declining at a very fast rate. Several tests are available in literature to test a data series for normality. It is emphasized that different tests are good at detecting different types of departures from normality. In this lecture, we are going to discuss many such tests. Key approaches to test for normality. Two main approaches are used in literature. The first one is called informal method, also called graphical method, such as plotting a histogram of the OLS residuals or any other data series, and also making a normal probability plot. The second method is called formal method, where we use some proper statistical or econometric test. Some of the famous tests that are used in literature to test a data series for normality are Skewness and the Kurtosis measures, the Jarque-Bera test of normality, and Kolmogorov-Smirnov test, among many others. Let's discuss these two methods one by one. So let's first discuss the informal method, histogram of OLS residuals. This method involves constructing an histogram of OLS residuals and seeing if it matches with the bell-shaped normal curve drawn with the same mean and same standard deviation as that of OLS residuals. This means that we need to calculate mean and standard deviation of OLS residuals, and then from the mean and standard deviation we can calculate this bell-shaped normal curve. Because normal distribution has two parameters, mean and variance, we have calculated the mean from OLS residuals as well as standard deviation. The square of standard deviation is variance, so we have two parameters with us. So once we have these two parameters in hand, we can construct a normal density curve, and then we can match the histogram of OLS residuals with this normal density curve. If there is a good match, then the OLS residuals are said to be normally distributed, otherwise not. This figure shows OLS residuals histogram with normal curve with same mean and same standard deviation as that of OLS residuals. The red line is the normal curve with mean equals to mean of OLS residuals and standard deviation equal to standard deviation of OLS residuals. And the histogram is represented by these blue bars. Roughly speaking, there is a good match between the residuals histogram and normal density curve. However, there is slight mismatch at this peak. The peak of histogram is somewhat higher than the peak of normal curve. The right hand side also shows some mismatch, but overall there is a good match between the two. Let's discuss the second informal method, normal probability plot. This method involves comparing observed cumulative distribution function, the CDF of data series or OLS residuals in our case, with the theoretical CDF of standard normal density with matching mean and standard deviation as that of OLS residuals. If the CDF of OLS residuals, which is also called observed CDF, matches with the CDF of normal, which is also called theoretical CDF, so if there is a match between observed and theoretical CDF, then the OLS residuals are said to be normally distributed, otherwise not. Figure shows observed CDF of OLS residuals versus theoretical CDF of normal with matching mean and standard deviation as that of OLS residuals. So this red line gives us theoretical CDF of normal with mean 0 because the residual series has mean 0, and the second component is the variance, which is square of standard deviation. And this blue line gives the observed CDF of OLS residuals. From this figure we can see that there is a good match between the two, although there is some discrepancy in the center, but overall a good match. So from this normal probability plot we can conclude that the residual series is normally distributed. So we have discussed the two informal methods. Now let's move to the formal method. The first one is using skewness measure. Since normal distribution is symmetric, that is equally spreaded around the mean, so one measure of assessing residuals for normality is to see if they are symmetric or not. Here in this diagram, 0 is the mean, and we can see that area to the left of the mean is same as area to the right of the mean, and the shape to the left of the mean, this 0 line, is same as shape to the right of this zero line. So the normal distribution, this bell-shaped curve, it is symmetric, so equally spreaded around the mean. To assess lack of symmetry, skewness measure is used. In this diagram we can see that the middle one is the normal distribution with no skewness. Here in this diagram we can see that the right tail is longer than the left tail, so it means there is asymmetry. Both tails are not equal in length. So this is the situation of positively skewed distribution or right skewed distribution, because right tail is longer than the left one. In this diagram the left tail is longer than the right tail, so this is called negatively skewed or left skewed. For normal distribution the value of skewness is 0. Theoretically this value is 0, but for sample data this value can be slightly different from 0. But as sample size increases, the value of skewness will converge to 0. Calculations of skewness measure. How skewness can be calculated? Let x be a random variable with mean mu and variance sigma square, then skewness is defined as expected value of x minus mu over sigma whole cube, which is also called third standardized movement. Please note that mu is being subtracted from x, so it means x is being centered here, and then this difference is being divided by sigma, so it means the x is scaled as well, so x is centered as well as scaled, so it means x is made standardized, and then the third power of this, and then the expected value, so it is called third standardized movement. Let's demonstrate how we can calculate skewness measure for some hypothetical data using MS Excel. Let x be a random variable containing 4 values 1, 2, 3, 4. First step is to calculate average of these 4 values, the mean, and next step is to calculate standard deviation of these 4 values. The mean is found to be 2.5 and the standard deviation is found to be 1.118. Next column, standardize this x variable by subtracting mean from each value of x and dividing this difference with the standard deviation. Name this column as z. So from this first value of x, 1, subtract the mean which is 2.5, so 1 minus 2.5 which is minus 1.5, and divide this minus 1.5 with this standard deviation 1.118. The answer is minus 1.342. And similarly 2 minus mean over standard deviation, 3 minus mean over standard deviation, 4 minus mean over standard deviation. Excel command to get result in this column is given here. So B2 minus B6 divided by B7. So B6 is the average value and whole divided by B7. B7 is the standard deviation. And I have used the dollar signs to fix both mean and standard deviation. Copy this command downward. B2 will change to B3 and then B4 and then B5. But B6 and B7 will remain fixed due to dollar signs used. And then in the next column take cube of all these values. So C2 cube, C3 cube and so on. And finally take the average of these 4 values. The average is 0. So this average is called the skewness. So this is how you can calculate skewness. In Excel you can use skew command to calculate skewness. Put an equal sign and type skew, and then within the parenthesis your data series range. In our case the data lies in cell B2 to B5. B2 is the first value and B5 is the last value. If skewness is 0 then the distribution is symmetric, the one shown in the middle. If skewness is greater than 0 then the distribution is right skewed, the one showed here, positively skewed or right skewed. If skewness is less than 0 then the distribution is left skewed, this one negatively skewed or left skewed. Now let's discuss the second formal method, which is Kurtosis measure. Another way to assess normality is to see if tails or peak of the distribution of OLS residuals match with the tails or peak of the normal distribution with same mean and same standard deviation as that of OLS residuals. This is done by using Kurtosis measure. For normal distribution, kurtosis is 3. Now let's discuss how we can calculate kurtosis measure. Let x be a random variable with mean mu and variance sigma square, then kurtosis is equal to expected value of x minus mu over sigma whole raised to power 4, and it is also called the fourth standardized movement. Let's discuss how we can calculate kurtosis using MS Excel. Take the same x variable containing 4 values 1, 2, 3, 4, calculate the mean which is the average, calculate the standard deviation, and then in the next column calculate the standardized variable, the same z variable, by subtracting mean from each x value and dividing this difference with the standard deviation, and finally calculate the fourth power of this variable z and take the average of these 4 values to get the value of kurtosis. So here is the command, average command, to calculate this mean, and stdev.p is the command to calculate standard deviation, and then the usual command to calculate the standardized variable z, and now c2 raised to power 4 to calculate the fourth power, and finally we took the average to calculate the value of kurtosis. Kurtosis in our case is 1.64. If kurtosis is equal to 3 then the distribution is mesokurtic or normal, so here the red one. If kurtosis is greater than 3 then the distribution is leptokurtic, the blue one. If kurtosis is less than 3, then the distribution is platical, take the green one. There is an alternative measure of kurtosis as well, that is called excess kurtosis, E for excess, K for kurtosis. Excess kurtosis can be calculated by subtracting 3 from kurtosis. Ek is equal to kurtosis minus 3. In Excel, you can use Kurt command to calculate excess kurtosis. Equal sign KURT B2 to B5. So this command will calculate excess kurtosis of the values containing in cells B2 to B5. Please note that there is no command in Excel to calculate kurtosis directly. However, you can use excess kurtosis formula to calculate the value of kurtosis. This is done by this formula: kurtosis is equal to excess kurtosis plus 3. This is obtained by shifting this minus 3 to the left hand side. So 3 is being subtracted here. When it is shifted to the left hand side, it gets added to excess kurtosis. So kurtosis is equal to excess kurtosis plus 3. Now it is easy to verify that for normal distribution or mesokurtic distribution, the value of excess kurtosis is 0. For leptokurtic distribution, the value of excess kurtosis is greater than 0. And for platokurtic distribution, the value of excess kurtosis is less than 0. So let's discuss the summary of skewness and kurtosis measures. To test OLS residuals or any other data series for normality, calculate skewness measure as well as kurtosis measure. If skewness is 0 or close to 0, then the distribution is symmetric. If kurtosis is 3 or close to 3, or excess kurtosis is 0 or close to 0, then the tails of the distribution of OLS residuals match with the tails of the normal distribution. This implies that the distribution of OLS residuals is normal. However, if any of the skewness measure or excess kurtosis measure is different from 0 or kurtosis is different from 3, then the distribution of OLS residuals will be non-normal. So for normality, skewness must be 0 or close to 0 and kurtosis must be 3 or close to 3. Or in other words, excess kurtosis must be 0 or close to 0. If skewness is 0 but kurtosis is different from 3, then it means the distribution is symmetric, but the tails of the distribution of OLS residuals are not matching with the tails of the normal distribution, which is also called the benchmark distribution. If skewness is different from 0 but kurtosis is 3, then it means the distribution is asymmetric, not equally spread around the mean, but the tails of the distribution of OLS residuals are matching with the tails of the normal distribution. Please note that for normality, the skewness must be 0 and kurtosis must be 3. If any of these two measures differs from its benchmark value, 0 in case of skewness and 3 in case of kurtosis, then the distribution will not be normal. So for normal distribution, skewness must be 0 and kurtosis must be 3, or excess kurtosis must be 0. Please note that in case of sample data, the value of skewness can be close to 0. It may not be exactly 0. Similarly, the value of excess kurtosis will be close to 0 and it may not be exactly 0. And the same holds true for the value of kurtosis, which will be not exactly equal to 3, but it will be close to 3. Let's move to the third formal method, the Jarque-Bera JB test. Instead of testing normality using individual skewness and kurtosis tests, Jarque and Bera proposed a combined test known as Jarque-Bera or JB test. The null hypothesis of JB is OLS residuals are normally distributed, and the alternative hypothesis is OLS residuals are not normally distributed. This null hypothesis is tested via JB statistic, which is given by this formula. JB is equal to T times skewness square over 6 plus excess kurtosis, which is kurtosis minus 3 whole square over 24, where skew is the skewness measure, kurt is the kurtosis measure, and T is the total number of observations. Please note that instead of kurtosis minus 3, you can simply add EK, which is excess kurtosis. So in different books, you may see that version of the formula. JB statistic follows chi-square distribution with 2 degrees of freedom asymptotically. Asymptotically means only in large samples. Its critical value can be found via critical value table of chi-square distribution, which is usually available in the appendix of most of the statistics and econometrics textbooks, or you can use Excel command as well. So put an equal sign and then type chi inv inverse. So chi inverse and within parenthesis alpha, where alpha is the significance level, which is usually taken as 1% or 5% or 10%. So 1, 5 and 10% are called conventional significance levels, and this df is called degrees of freedom, and degrees of freedom is fixed at 2. For alpha equal to 5% and degrees of freedom equals 2, which is fixed, critical value is calculated as equal sign chi, I and V, and within parenthesis 5%, which is 0.05, and comma 2. 2 is the degrees of freedom. Now let's discuss the decision about rejection or non-rejection of null hypothesis. If JB calculated is greater than critical value, it means the calculated value of JB statistics calculated via formula that is shown in the previous slide is found to be greater than the critical value which is obtained via this command. Then we reject the null hypothesis at 5% significance level because this critical value is calculated at 5% significance level. So please note that whenever we reject a null hypothesis, we need to mention the significance level, that at what significance level this null is being rejected. Currently we have calculated the critical value at 5%. That's why we are mentioning that reject null hypothesis at 5% significance level. But if the critical value is suppose calculated at 1% instead of 0.05, suppose you have used 0.01, and if JB calculated is found to be greater than 1% critical value, then reject the null hypothesis at 1% significance level and conclude that OLS residuals are non-normal. So it's up to you which significance level you use. So generally all these three significance levels are used: 1%, 5% and 10%. And if JB calculated is found to be less than critical value, then do not reject null hypothesis at 5% significance level and conclude that OLS residuals are normally distributed. Instead of using the critical value and comparing the calculated value of JB statistic with the corresponding critical value, one can also use the p-value method to test the validity of null hypothesis. Excel command for calculating p-value is equal sign chi dist and within parenthesis calculated value of JB statistic, which will be calculated via formula shown in the previous slide, and comma df, where df is equal to 2 fixed, which is the degrees of freedom. Now let's discuss the decision regarding rejection or non-rejection of null hypothesis using this p-value method. If p-value is less than significance level, 1% or 5% or 10%, then reject the null hypothesis of normality at chosen significance level, 1% or 5% or 10%. Suppose here you have selected 1%. So then if the calculated p-value calculated via this command is found to be less than 1%, 0.01, then we will reject the null hypothesis of normality at 1% significance level. And if suppose calculated value of p calculated via this command is found to be less than 0.05 or 5%, then we reject the null hypothesis of normality at 5% significance level. Similarly, if the calculated p-value calculated via this command is found to be less than 10% or 0.10, then we reject the null hypothesis of normality at 10% significance level, and we conclude that OLS residuals are non-normal. And if p-value is greater than significance level, 1% or 5% or 10%, then do not reject the null hypothesis of normality at chosen significance level, 1% or 5% or 10%, and we will conclude that OLS residuals are normally distributed. So this is how the decision regarding rejection or non-rejection of null hypothesis is taken using p-value method. Let's discuss an important note on critical value of JB statistic. Since JB statistic has chi-square distribution with 2 degrees of freedom asymptotically, this means that the distribution of JB statistic is valid only in large samples, implying that when sample size is small, then the distribution of JB statistic may not be chi-square, but it may be some other non-standard distribution other than chi-square. This means that the critical values and the p-values calculated previously based on asymptotic distribution, which is chi-square, they may not hold true in small samples. And the conclusion regarding rejection or non-rejection of null hypothesis may be misleading in finite or small samples. Please note that the concept of large sample is subjective. In some cases, a sample of 100 observations will be considered as large, and in some other cases, a sample of even 1000 observations will not be considered as a large sample. Generally, it is advised not to use critical values based upon asymptotic distribution. So how to overcome this issue of finding critical values in finite samples or small samples? This can be done by calculating a new set of critical values at 1%, 5% and 10% significance levels for small samples by carrying out simulations. The process of carrying out simulation is explained in the empirical example and the Excel demonstration in forthcoming slides. Let's demonstrate all this with the help of an empirical example. Consider a multiple linear regression model relating composite SAT scores CSAT with the percentage of students who appear in the SAT exam % and expenditure per pupil by the government expense. The data consists of 51 states of US, and here is the multiple linear regression model where CSAT is the dependent variable, % and expense are 2 independent variables, epsilon is an error term, and beta 1, beta 2, beta 3 are regression coefficients, and the sample contains 51 observations. Our objective is to estimate this multiple linear regression model via ordinary least square method, the OLS, and test the residuals obtained from this regression model for normality using all methods discussed in this lecture. Specifically, we will focus on the two informal methods and the two formal methods that we have discussed. So first one is constructing histogram of OLS residuals and matching it with the bell-shaped normal density. The second one is by constructing normal probability plot, and the third one is skewness and kurtosis measures, and the fourth one is the Jarque-Bera or JB test. So let's move to the Excel sheet for demonstration.